All right, so in 4.6, we're doing the variation of parameters. We have coefficients out here. If they're constant, this technique will follow. If they're non-constant, this technique still works. And in a minute, I'll point out why this may not help us as much when there's x's in there, because we still got to find the homogeneous solution. So let's consider this equation in general. The right-hand side is non-zero. In order to simplify this derivation of the solution, what I'm going to do is, instead of solving this equation, I'm going to divide through by a sub x and write it like this. You've seen this modification before. Remember whenever we did linear equations that were first order, right? And I had a1 of x y prime plus a0 of x y equals b of x. This was back in chapter 2. I divided through by a1 and I wrote it as y prime plus a0 over a1 y plus, or equals, let me slow down, b over a1. And then instead of calling this a naught over a1, I called this p of x, and I called this q of x. And that's then where I use the integrating factor. Mu is e to the integral p of x dx, and so on. Went on from there. That was the linear first order case. So I'm doing the same thing in this linear second order case in the special technique known as variation of parameters. Just divide through by whatever the coefficient is out front. If you've got something other than a 1 right here, divide through by it. And then we're going to call this p, we're going to call this q, and we're going to call whatever we end up with on the right-hand side f. Okay, so now our goal is to find the particular solution. We're going to assume that we can find the homogeneous solution. This is where it's not possible yet for us to do this if there were x's in front of the y's. We don't have a technique that gives us the homogeneous solution. That is, if the right-hand side was 0, if I had like x squared here, maybe an x here, and maybe a 1 here, I don't know how to solve that yet. That's actually another technique that we may or may not cover later on. So this assumption means that we assume that we can find two linearly independent solutions to the homogeneous case. So let's assume that we can do that. So for now, we're kind of assuming that these are constant, because we know how to do it when those are constant. Okay, now our goal is to try to find a particular solution. So in this case, my general solution has a constant here and a constant here, C1 and a C2. I'm going to make another educated guess. So even though I called the method of undetermined coefficients the educated guessing method, this is also kind of guessing. I'm guessing that the form of my solution is going to look like something that's a function of x times my y1 of x plus something of x times y2 of x. I'm going to assume that I can create a combination of my two known solutions to the homogeneous case by finding maybe something that goes out in front that are the unknowns. So I'm looking for u1 and u2 that will satisfy equation 2. I know y1 and y2. I'm going to assume I can find it. Now can I find u1 and u2? And that's what the variation of parameters methods does, is it sets up equations to solve what u1 and u2 would be so that it satisfies the starting equation. I get an f of x on the right-hand side. So let's start simply. I'm going to rewrite this as u1 y1 plus u2 y2, just to get rid of the of x's so that it's not too messy. But I'm going to remember that all of these are functions of x. So let's say yp is equal to u1 y1 u2 y2. Now take the derivative of that. So since each of these are functions of x, I got to use the product rule on each one. So I get u1 y1 prime plus u1 prime y1. That's first times the derivative of the second plus the second times the derivative of the first. And then do that for the second term as well. It's going to give me u2 y2 prime plus u2 prime y2. So I want to group these together. I'm going to put my U1, oh, sorry, I messed up. No, so I'm right. I want to put my U1 Y1 primes and my U2 Y2 primes together. I'm going to put these together. I'm basically grouping them by what's primed. So I have a U1 Y1 prime plus U2 Y2 prime. I'm reordering, that's all I'm doing. U1 prime Y1 plus U2 prime Y2. Okay, now I'm going to take a step that seems to come out of the blue, but when we finalize this in a minute, it'll make sense why. I am going to try to simplify this derivation a little bit. I'm going to say, let's set this equal to 0. That's going to be my first constraint on my y, or my u1 and my u2, as I'm going to set that equal to 0. Firstly, the main reason is I just want this term to drop out. 2, since u1 and u2 are unknowns, I'm going to apply constraints to them so that they will possibly have a solution to this differential equation. Later on, I'll see that I'll get a second condition, so I actually have 2 equations with 2 unknowns that both depend on u1 prime and u2 prime as being my unknown. So if I set that equal to 0, this term just drops out. So all I've got left for my yp is u1 y1 prime plus u2 y2 prime. All right, so same thing again. Let's take the derivative of that. Applying the chain rule, not chain rule, the product rule, what do we get when we take the derivative of this?
U1 Y1 double prime plus
U2 prime.
Let's do this one completely first.
U1 prime Y1 prime
Plus U2 Y2 double prime plus U2 prime Y2.
Okay. All right, so using this here, and this here, I'm going to plug all of those into equation 2 up here. Okay? I'm going to plug it in yp double prime here, yp prime here, and yp right there. Okay? So on the left-hand side, if I start with yp double prime plus p, yp prime plus q, yp, that's going to give me, just plugging these 3 things in, there I get u1 y1 double prime plus u1 y1 prime, u1 prime y1 prime, plus u2 y2 double prime plus u2 prime y2 prime, plus p times, now yp, which will be u1 y1 prime plus u2 y2 prime, plus q times, make sure these are times, these aren't p of, that's q times and p times, just u1 y1 plus u2 y2. Okay, now I'm going to group all of the u1s, not the u1 primes, but the u1s together. So the u1 here, the p u1 y1 prime, and the q u1 y1 here. If I distribute this p, of course, and this q, and then I put all of those together and factor out the u1, I'm left with y1 double prime plus p y1 prime plus q y1. Right? Again, I'm distributing the p, so these terms have a p in them. This term has a q in them. If I factor out the u1 from each of those three, I'm left with y1 double prime plus py1 plus qy1, py1 prime plus qy1. So that term's taken care of, that term, that term. I'm also going to group all the u2s together. And if I do that and factor out the u2, I get what?
U2, y2 double prime, y2 double prime, and y2 prime.
Well, I got a p in there because of this.
P, y2 prime.
y2 prime plus
Q.
qy2. And then what's left behind after I've done those three terms? Just this one and this one, right? u1 prime y1 prime plus u2 prime y2 prime. Okay, so question, what is this right here equal to? You're close, though. That y1 is not a particular solution of 2. What is y1?
General solution.
General solution to the
Homogeneous.
homogeneous equation. Homogeneous means what?
Equal to 0.
Equal to 0. Right? To say y1 is part of the general solution to the homogeneous version of this means that if I were to apply y1 in here, plug y1 in here, and plug y1 here, I get 0. That's exactly what this is. y1 double prime plus py1 prime plus qy1, that's 0 since y1 and, of course, y2 solve the homogeneous version of equation 2. Now, all we've got left is this right here. Now, what is that equal to? Well, come back to what I have written right here. I'm looking for yp. Yp is a particular solution, which means it's actually a solution to 2. So what is this equal to then? If yp is a solution to the actual equation 2 up here, then if I plug in yp into this, I better get f of x. Okay? So here's what I've got. I'm just going to write it down here at the very bottom. I know you're running out of space. But I've got u1, y1, both prime, plus u2, y2, both prime, equals my f of x. Okay. Now I'm going to highlight it in purple just so it stands out. Look at this equation here and this equation here. y1 and y2 are known. U1 and u2 are unknown. You basically now have a 2 by 2 system where your unknowns are the u1 prime and the u2 prime. So I'm going to write it as a 2 by 2 system. So I've done at the top of the next page for you, right there. Yes.
Value of back high. There, how do we know that we can change a little high? A little high. How do we can equalize set that to 0 without changing the value of yp prime p?
It does. What I'm doing is in fact, if I didn't set that equal to 0, then this yp double prime is much more complicated. So what I've done is I've invented one more constraint, one more equation I've just created to apply to U1 and U2, right? If I apply this constraint and this constraint, I'm going to try to find a U1 and U2 that satisfy both of these simultaneously. If they do, right, if the U1 and U2 satisfy this, and the U1 and U2 satisfy this, then YP solves the equation. But I've got to find the U1 and U2 that makes this work, and the U1 and U2 that makes this work at the same time. But now, since I have two equations and I have two unknowns, I'm going to be able to solve them. Again, in this equation right here, I don't want to draw all over it, but you see the y1 and the y2, the y1 prime, the y2 prime, we're assuming we know. It's the u1 and u2 that we're trying to find. Okay? So when you see a 2x2 system, we can do this in our heads because we know something called Kramer's rule. Yes, there are other ways to solve this, but Kramer's rule turns out to be the easiest way to write down the solution to this. Do you remember Kramer's rule? It's the big H. Okay, so you got a determinant on top and a determinant on bottom. To apply Kramer's rule, I'm going to set W equal to the determinant of the coefficient for this system. The known coefficients would be y1, y2, y1 prime, and y2 prime. Keep in mind, these have x's in them. These are functions now. Does that look familiar to you at all? A matrix that has on the first row the functions and on the second row its derivative. Yeah, we gave it a name. Starts with W, which is why I called it.
Wronskian.
Caleb got it back there too. Wronskian. Shows his ugly head again. That's the thing that is used to check if functions are linearly independent. W1 is to take the right-hand side of the system, so 0f, and put it in the first column. Y2, y2 prime. And W2 would be y1, y1 prime, 0f. Then, the solution is the first unknown, u1 prime, will be whatever this w1 is here over this w, and u2 prime would be w2 over w. Now note, both of these equations on the right-hand side have x's in them, no y's, they just have x's. So, if we integrate each of these equations, we will have found a u1 and u2, and that u1 and u2, if we stick them as coefficients to my y1 and y2, then this dude right here is a particular solution, which is what we're looking for. So there's really no guessing. The only guessing we did was to assume that this form would be a particular solution and that I could find a u1 and a u2, that when I plug them in there, this resulting sum of terms is a particular solution. Okay, so your final solution would look like a C1y1 plus a C2y2, right, where C1 and C2 are your parameters that would eventually be determined by your initial conditions, plus then your particular solution, which is u1y1 plus u2y2. So that's our technique.
That first one's a C1Y1, right?
Yeah. So what do I have to remember to do this? of all the stuff we've done on page 1 and 2, that's it. That's the key. That's what we've got to know. Because once we get this, then we integrate and we find our U1 and our U2. Notice, by the way, we've got to find Y1 and Y2 first. So our process is going to be very similar to what we did in 4.4, which is find the homogeneous solution first, then build these determinants to find our U1 and our U2. Now, the kink in this process is the integration step. You may or may not be able to actually integrate the resulting functions. Whereas with the method of undetermined coefficients, there's no integration step. There's only solving for these coefficients, which, while tedious and lengthy, is guaranteed to have an answer that you can do. So it's not that one method is necessarily better always than the other. They both have their advantages and disadvantages. All right.
Sugar. The one at the bottom.
So the rest of this is we're going to do 3 different examples. I'll do 2 of the second order and then show you this generalizes up to even third order and higher. All right, so here's one that we could not do with the method of undetermined coefficients because we don't have a guess when we have a tangent on the right-hand side. None of our forms, all of our forms dealt with polynomials, exponentials, and sines and cosines. Tangents are products because when you take the derivative and second derivative, the secant guy shows up in all his glory. So
Did we do it as sine or cosine?
no, because then the derivatives turn into quotient rules, which are also very, very messy. So there's no good general format to get a method of undetermined coefficients to work with something. Even though it's a very simple looking guy, there's no good guess that works with the method of undetermined coefficients. So let's first of all start by finding our y sub h. In this case, what is our characteristic polynomial?
X squared plus 1. It's m squared plus 1.
I've been using m's for roots, right? Second derivative, coefficient is 1, so 1m squared. There's no first derivative, and so there's a 0 derivative, so it's just plus 1 equals 0. So m is square root of negative 1, plus or minus, so plus or minus I. So that's where like a is equal to 0 and b is equal to 1 in your a plus or minus bi. Remember your form for those are e to the ax cosine of bx and e to the ax sine of bx. Those are your 2 fundamental solutions. So yh would be c1 cosine of x plus c2 sine of x. I'm going to call that my y1. I'm going to call that my y2. Okay, so now our yp, if we're going to use variation of parameters, we assume yp is some function u1 times y1, which is cosine of x, plus some function u2 times y2, which is now sine of x. y1 is cosine of x, y2 is sine of x. I'm just going to write it off here so I have it handy. Now I need to write down my w, my w1, and my w2. What's the Wronskian for y1 and y2? Put them on the first row. What goes on the second row?
Negative sine x cosine x.
The derivatives, negative sine x cosine x. Forward minus back diagonal. Cosine squared of x plus sine squared of x equals 1. That's easy. Now w1. Remember W1, we replace the first column with 0 and then the right-hand side, the function, which is tangent in our case. So 0, tangent of x, and then leave the second column the same. Sine x, cosine x.
So, I'm just kidding.
So this is negative sine x times tangent of x. You want to simplify that a little bit?
What negative?
4 diagonal minus back diagonal. Tangent is sine of x over cosine of x. I can either do this now or I can do it when I'm integrating. I'm just going to go ahead and do it now. Let's just write this as minus sine squared of x over cosine of x. Actually, we'll do a little now and do a little later. You could have just left it right here for now. W2. Now cosine of x, negative sine x, 0, tangent of x. Four diagonal minus back diagonal gives me cosine of x times tangent of x, which does simplify nicely because the cosines cancel, and that's just sine x. Okay. And again, we did all this because we're just applying Kramer's rule to that system I derived earlier. I know then that U1 prime is W1 over W, or negative sine squared of x divided by cosine of x. So when you've got u prime equals this, you just take the integral. U1 will be the integral of negative sine squared of x over cosine of x dx. Now, that's actually not too hard of an integral. We can simplify that with some trig identities. How would you simplify that to a thing that we could then integrate?
Well, I was thinking you said, no,
If you let u be cosine, then you've got an extra sign on top that you got to do something with. Because one of the signs goes with the dx to become du, but you still got a sine of x left over. I was thinking, what if we took this and replaced sine squared of x with 1 minus cosine squared? Because then you got this multiple thing on top over a single denominator can separate it into separate fractions, and maybe each one of those will simplify. In fact, on one of them, the cosine will cancel with the cosine on bottom. If I distribute the minus, this becomes a cosine squared of x minus 1 over cosine of x, which is, split it up, and I get cosine squared over cosine, which is cosine, minus 1 over cosine, which is secant. So the integral of cosine is sine. Anybody remember the integral of secant? It's a mess. It's a log secant plus tangent. We did this one in Cal 2 just the other day. So Matt, you remember, right? Natural log of secant of x plus tangent of x. I look it up on a table, which I always have handy.
Yeah, I saw the Cal 2 table. Can I get one of those sheets?
Sure. I'll post it in Blackboard and you guys can print off your own copy.
It's pretty nice.
It's just a whole bunch of formulas
Yeah, I know.
that's like all your trig identities, all your differential or derivative, basic derivative formulas, and like table of 100 integrals.
You should tell the Antonio about that.
Do what?
The Antonio. Tell me it exists.
You can have it. I'll let you have it. I even let you use it on a test if you want to.
Wait, is that,
Natural log of the absolute value of secant of x plus tangent of x. That's my u1.
why did you flip the,
The order
yeah, shouldn't, oh, it's negative.
is the minus, yeah. I think I said that, but I did it really fast.
So did you, oh,
So I have a minus sine squared, so a minus of 1 minus cosine squared. So I just distribute the minus, that gives me a minus 1 and a plus cosine squared. So I
so
just,
whenever you did the group, like you when you basically separated it?
yeah, I mean, it's the opposite of when you add fractions with a common denominator, right? A over C plus B over C is A plus B over C. You can also go this way. You have A plus B over C, you can write it as A over C plus B
Yeah, I
over
was
C.
just wondering what, like, that was, so,
That's me splitting.
okay.
That's how I visualize it in my head. Now you know, U2 prime would be W2 over W. This one's easy. Sine of x. So U2 would be the integral of sine of x dx, which is negative cosine x. Now, I'm leaving off the plus c's on purpose. You may be kind of cringing a little bit because I'm doing an antiderivative, an indefinite integral without plus c's. But I don't need all possible solutions to this. I only need one. I only need one particular solution. So I'm ignoring those parameters because I already have my general solution taken care of with the C1y1 and C2y2. I don't need extra c's here because I'm only looking for one single particular solution. But now I've got a u1 and a u2. So my yp is u1 times y1. So sine of x minus natural log of the absolute value of secant of x plus tangent of x times y1. All right, by the way, I'm going back to this right here, right, to write my yp. My y1 was cosine x. So u1, y1 is, this is my u1 times cosine of x plus my u2, which is negative cosine of x, times y1, which was sine of x. So u1, y1, u2, y2. And actually that simplifies a little bit because if I distribute this to these two things,
You get a plus cosine x.
I get these and these canceling, right? So this cancels with these, and I'm left with yp is just negative natural log of secant of x plus tangent of x times cosine of x. So then what's the general solution? What's the final y?
Oh, C1 cosine of x plus C2 sine of x minus natural log of secant x plus tangent x cosine x.
There it is. All right, so make sure you understand the process. Don't get bogged down in too many of the fine details here. The point is that we first find YH, assign Y1 and Y2 to be those two functions, then use them to solve that system, namely by using the Wronskian and then the W1 to W2. U1 is W1 over W, U2 is W2 over W. Actually, U1 prime is that, U2 prime. We have to integrate to find U1 and U2. Once we found those, we plug them back in and get a particular solution, and we plug our particular solution into YH plus YP to get our full solution. And we could not have solved this example using the method of undetermined coefficients. All right, any questions? We're going to just do another one, just for practice sake.
Wow, it's busted out. There's much less space for this one. It should be easy.
I just made less space because you're getting good at it now. By the way, this is one you could use the method of undetermined coefficients for.
Sorry, can I keep up just real quick? I almost have
Gladly. On the next one, I went ahead and threw it in there so you could kind of get a feel for which one you think would be your favorite, your choice, because this one's one that you will actually be able to do either way, right? Because it's a polynomial times an e to a power. All right, so first of all, what's y sub h? Are you to the point you can do that in your head yet? And it's a double root, right? So your YH would be C1 e to the...
E to the negative 2.
It's
or
positive.
E to the 2x. I guess we're going to x is C2 plus C2x e to the 2x.
Yeah, I switched to x's in this section because the book does x's throughout this entire section, which annoyed me. So
I know, I was, on my homework, I was getting frustrated, and then I realized
Keep it
I
track.
had T's in there.
I mean, to me, I don't know why we spend time in x at all in this section, because most of these models are
Time.
dynamical models. They're evolving over time. Right, so x e to the 2x. All right, so here's my y1. I'm going to call x e to the x my y2. Okay, so w. Will be e to the 2x, x e to the 2x. Derivative of e to the 2x is 2e to the 2x. Derivative of x 2e to the 2x is product rule, so 2x
e to the 2x
dx.
plus e to the 2x.
Forward diagonal minus back diagonal. By the way, if you don't have space, feel free to use the back of your pages. That's why I did that. Don't feel like you have to write so small as I do. I get a 2x e to the 4x plus e to the 4x minus 2x e to the 4x. Boom. Boom is e to the 4x. Nice. Now W1. First column is
0, x plus 1 e to 2x.
blah, blah, blah. It's too lazy to write it. Because it's 0 anyways. So x times x plus 1 e to the 4x. But there's a minus up front. W2. E to the 2x. 2e to the 2x. 0. Okay. So U1 prime is W1 over W negative x times x plus 1 e to the 4x divided by e to the 4x gives me negative x times x plus 1 or minus x squared plus x. So then,
Is it minus x squared?
yep. U1 prime is the integral, negative x squared minus x dx. So U1, negative 1/3 x cubed minus 1/2 x squared. We got our U1. U2, W2 over W, x plus 1 e to the 4x, divided by e to the 4x. E to the 4x is cancel. So x plus 1. U2 prime is the integral of x plus 1 dx, which is 1/2 x squared plus x. Yp then is U1 y1 plus U2 y2. So, negative 1/3 x cubed minus 1/2 x squared times e to the 2x plus 1/2 x squared plus x times y2 x e to the 2x. I get 1/6 x cubed e to the 2x plus 1/2 x squared e to the 2x.
I'm gonna say
Some algebra occurs here. It's out. You can actually do this in your head. If you distribute this, right, then you get an x cubed. So you actually have a minus 1/3 x cubed e to the 2x and a 1/2 x cubed. So minus 1/3 plus 1/2 is 1/6. And then the x squared, you're going to have a minus 1/2 plus 1 gives you a plus 1/2. So your final answer, y, is c1 e to the 2x plus c2 x e to the 2x plus 1/6 x cubed e to the 2x plus 1/2 x squared e to the 2x. And then at least one problem in your homework is actually an initial value problem. I didn't do that here, but initial value problems are where I give you like the y at 0 and the y prime at 0, and you have to find C1 and C2. So there still could be more work to be done after this. Okay, so before we flip the page, before we kind of go through it to the bottom here, let me point out just one kind of minor detail. As a refresher from your method of undetermined coefficients. Do you remember whenever we did the method of undetermined coefficients, what we started with was a guess of what y sub p would look like whenever we had something like this? If you were to do the method of undetermined coefficients, your first guess would be, since it's a linear times e to the 2x, you'd do ax plus b times e to the 2x. But there's a problem with this guess. Do you remember why that's a problem?
Because it's probably whatever.
In fact, both of them are. b e to the 2x matches this one, and even x e to the 2x matches this one. So you can't use either one of these, so you need an extra 2 x's in there, an x squared. So actually what your guess is ax cubed plus bx squared e to the 2x. In the method of undetermined coefficients, what you then do is take the derivative of this, the second derivative of this, plug it all into this function here, and then solve for a and b. If you did that, guess what you get?
The C, or U.
Do you see them? I mean, this right here and this right here are these terms. So if you were to do the method of undetermined coefficients, take the derivative twice, plug it in here, simplify it, set the left-hand side equal to the right-hand side, you'd get a turns out to be 1/6, and b turns out to be 1/2. Which matches exactly what we get from the variation of parameters method. Completely different techniques, but end up in exactly the same place. Okay? Okay, last thing is we can take this to any order linear differential equation and use this technique. The only difference now is when we build this system, this equation right here. Say, for example, this was a cubic. Say we had 3 derivatives in there instead of just second derivatives. Way back up here when we were deriving the method, and I set yp equal to u1 y1 plus u2 y2. Now we're going to have 3 of them. It would be u1 y1 plus u2 y2 plus u3 y3, because it's a third order. If it's nth order, there'd be n of them. I take the first derivative and I set this thing equal to 0. What I then do is take the second derivative and I set the next thing also equal to 0. And I keep going until I get to the third or whatever the highest derivative is. And then I go through this process. And what you will end up with, if you repeat that process for higher order systems, is this system right here. I keep setting a bunch of things equal to 0 until my very last one I just set equal to, it ends up being equal to f of x. So notice the structure of this thing again. Going down this way, my variable, my unknowns, are the u's. And by the way, there's a typo, 2 of them. This should be 2. This should be n. And then here are the coefficients. Okay? So your W equals this thing with all the blues in it, right? Which is still the Wronskian. That's the W that's down here. And then the WK is, and I'm going to, just for lack of a space to write it all the way out, you take your original W, I don't know how many, I'm going to do 4. Whatever. And you replace one of the columns with, what I'm going to do is purple. Right? Boom, 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 boom. That's the kth column. Okay, W1, we replace the first column, W2 replace the second column, and so on. But that's what you do to get your numerator up here. And then you integrate to get your particular solution. So this thing generalizes, but the thing that you got to keep in mind when you generalize is that the column that you're replacing with is all zeros and then F. And it comes from the way that we derive it. Okay? So let's do a third order one in the same way that we did a second order one. And write small, you need the whole page. All right. What's your characteristic polynomial?
M cubed plus M.
Which means m times m squared plus 1 equals 0. So what are my solutions?
0 and plus or minus I.
Okay. So what would my YH look like if your solutions are 0 plus or minus I? This is like e to the 0x, right? Which is just
C1 plus C2 cosine and C3 sine of it, or sine.
exactly. So my y1 is 1, my y2 is cosine of x, and my y3 is sine of x. It's 1 because it's e to the 0x, in case you didn't see that. So, W. 1 cosine x, sine x. Take the derivative, 0, negative sine x, cosine x. Take the derivative, 0, negative cosine x, negative sine x. Now you can either use a shortcut for 3x3s, which is all the forward diagonals minus all the back diagonals. In my mind, what I'm seeing is the cofactor expansion we learned in linear algebra. It's the fastest way to do this. If I expand along this column right here, do 1 times its minor, plus 0 times its minor, plus 0 times its minor. Do you remember doing minors, cofactor expansion? You have to remember the plus, minus, plus signs. But in this case, it's just going to be 1 times negative sine x, cosine x, negative cosine x, negative sine x, which is 1 times sine squared of x plus cosine squared of x, which equals 1. Be aware, I am unintentionally creating a false sense of security by giving you examples where the Wronskians are all nice and simple. That's not always the case. In the real world, in the wild, they're not always nice and simple. They're going to be pretty nice in your homework. But you can just imagine these things could get messy. And then W1 over W could be a big nasty thing that depends on X. That's very difficult to integrate. Okay? So just because we're looking at simple problems here doesn't mean they're always that way. But you've got now a fairly robust technique to be able to handle these. All right, so now we take 0, 0, tangent x, cosine x, negative sine x, negative cosine x, sine x, cosine x, negative sine x, which will be, I'm going to do the cofactor expansion again. I get a 0, minus plus tangent x times cosine x, sine x, negative sine x, cosine x, which gives me tangent of x times cosine squared of x plus sine squared of x equals, that's again 1, so just tangent of x. W2, Nope, I don't think so. 0, 0, tangent of x. And then sine x, cosine x, negative sine x. I get 1 times the the determinant of 0 cosine tangent negative sine, which actually just gives me a negative tangent of x times cosine of x. All right, 1 times this determinant here, which is just that. And by the way, the cosines cancel since tangent is sine over cosine. You just get a negative sine x for W2. W3, 1, 0, 0, cosine x, negative sine x, negative cosine x, and 0, 0, tangent. So 1 times its minor, which is negative sine times tangent, gives me a negative sine x, tangent x. We saw before, that's negative sine squared x over cosine x. Actually is cosine squared of x minus 1 over cosine of x, or cosine of x minus secant of x. Just repeating what I did before, because I recognize this thing as 1 minus cosine squared, and then distribute the minus sign, and then split this thing up. Excuse me. U1 prime is
Tangent of x.
just tangent of x. So U1 is the integral of tangent of x, which is the log of the secant of x. U2 prime is W2 over W, which is negative sine of x. So U2 is integral negative sine of x dx, which gives me cosine negative. Nope, just positive. U3 prime is W3 over W, cosine of x minus secant of x, all over 1. So U3 is the integral cosine of x minus secant of x dx, or sine of x minus the log of secant of x plus tangent of x.
The integral of tan x,
Did I have it wrong?
I think you can write it 2 ways, right? One should be the
It's very possible. I don't know what.
negative natural log of cosine x.
Yeah, it's the same thing, because natural log of x to the m is m natural log of x. So if you have natural log of secant, which is 1 over cosine, or cosine of x raised to a negative 1, you can pull the minus 1 out front. Yeah. So either way, would not be wrong and should be counted correctly because of the way that it uses Mathematica to check your answers on the homework. Emphasis on the should. All right, so yp is now natural log of secant of x times 1. Y1 is 1. Plus
Cosine squared x.
cosine of x times cosine of x. So sure, cosine squared of x. Plus sine of x minus log of secant of x plus tangent of x all times sine of x. Which we could then distribute, right?
Right, and then you get cosine x plus sine x.
Exactly. So you actually have log of secant of x plus 1 minus log of secant of x plus tangent of x times sine of x. Right? Because of the sine squared plus cosine squared. Become that 1. So your final y is C1 plus C2 cosine x plus C3 sine x plus the natural log of the secant of x. Minus log of the secant of x plus tangent of x sine of x.
Couldn't you? I don't know, see that multiply. If you tried to separate that log further to get rid of the secant.
Right, you can't because log of a sum doesn't simplify. Log of a product is sum of logs, but log of a sum is nothing, it's just itself. My was I made something disappear intentionally. Something's missing. The 1, why did I just drop the 1?
There's a C1 arbitrarily.
I absorbed it into the arbitrary constant C1. Technically that's like a new C1, but it's still just a constant, right?
Mm-hmm.
So just absorbed into there. I mean, it's not wrong the other way, but realize that every time you solve for a C1, C2, and C3, that 1's going to add to the C1, whatever's there. So you might as well just solve for that 1 constant instead of that constant plus 1. That's it. That's variation in parameters. Let me point out one thing, though. What's great about this method is that if we ever came up with techniques, which we can and may spend a little time doing, to solve the kinds of problems where there are x's in here, that as long as you can find the y1 and y2 for the homogeneous case, the variation of parameters method is exactly the same. So it's not restricted to the constant coefficients case. But the constant coefficients case are the ones that we can easily find y1 and y2. I'll look at at least one example. I don't know if I will. I may be post a video. We'll decide between now and Thursday if I'm going to show you the Cauchy-Euler equations or not. I've never taught them before, but a few years ago, one of our students went off to graduate school. It's in mathematics. And came back and had to ask me a whole bunch of questions about the Cauchy-Euler equation because they were covering it in one of their classes and he hadn't seen it. It's like, so this is the class where you would have seen it if you run into it down the road anywhere. And it was actually an engineering course he was taking. It wasn't just straight math graduate level stuff. So I'm torn. All that being said, 4.6 homework is assigned. It is due on Thursday. Be sure you get your 4.4 done today. And then we'll get close to wrapping up what we're going to test you over this week. And then we'll go to spring break, and then we'll come back and take a test either when we get back or the week after. Probably the week after we get back. But that means I'm going to cover new stuff, but I think you still would rather not take a test as soon as you come back. So we're done, dismissed. We'll see you guys next time. I just gave you back 3 minutes. I think we're almost square.